In this video, I'm going to cover everything you need to know to solve one-dimensional kinematics problems that show up in the context of an algebra-based introductory physics course. They'll usually show up in the first semester of Physics 1, the mechanics portion of the course. So you'll probably be asked a bunch of problems like you have some object here moving in this direction with initial velocity vi, and it's accelerating at say a meters per second squared, and delta t seconds later, how far has it gone? Or you might be asked something like someone's driving a car and they're going at say vi meters per second, and they jam on the brakes and decelerate at a meters per second, and they come to us, and you might be asked, how long does it take for them to come to a stop? Or you might be asked, how far do they travel before they come to a stop? In any case, the quantities you'll be dealing with are initial velocity. So these are the 5 quantities that you'll be concerned with. Initial velocity, final velocity, acceleration, displacement, and elapsed time. So initial velocity here, let me make a quick correction. Initial velocity, it's often noted v with the subscript I. Final velocity, is denoted v with a subscript f. Acceleration is usually denoted a. Displacement is denoted d. And elapsed time is usually denoted delta t. And sometimes you might see v naught, like v sub 0 for initial velocity. And sometimes you'll see delta s for displacement. But here for initial velocity, we're going to be using v subscript I, and for displacement, we'll be using d. Just going to erase this real quick. And in the context of an algebra-based physics course, we're going to assume that acceleration is some constant. So something will accelerate, speed up with positive acceleration, or decelerate with negative acceleration. But the rate at which it does so will be constant. It will be uniform throughout the entire process that you're considering. And that's really the situation in which the formulas that I'm going to derive actually hold. So I'm sure you know that displacement is the average velocity times elapsed time. So it's basically if something's moving in this direction, and it's moving at an average speed of 50 miles an hour, and or we'll say meters per second, 2 seconds later, you can expect that it traveled, well, let's say v average equals 50 meters per second, and you want to know how far it traveled in 2 seconds. Well, your displacements, your 50 meters per second times your 2 seconds, and that's 100 meters. But what if that velocity is changing? So what if this thing is, it's accelerating or decelerating? Trying to erase this here. What if this is changing? Then in the situation where acceleration is constant, the average velocity is equal to the initial velocity plus the final velocity over 2. So this is the average velocity, and you're again multiplying by the elapsed time. And so we have 4 quantities here: displacement, initial velocity, final velocity, and time. And you saw that all of these problems I'd mentioned earlier deal with 5 quantities: initial velocity, final velocity, acceleration, displacement, and elapsed time. So, but in any of these formula that we're going to derive, you'll have 4 of these 5 quantities. So encapsulated here, this final velocity is acceleration. It's a function of both initial velocity and acceleration, right? So let's say we wanted a formula that just related displacement, initial velocity, acceleration, and time, and we wanted to somehow do without this final velocity. Say we were given a problem. Say we're given problem asking for displacement and we're given acceleration, elapsed time, initial velocity. Yeah, just those 3 quantities: acceleration, elapsed time, and initial velocity. But we're not given the final velocity, and we're asked for displacement. So we're going to have to find a formula that relates displacement, initial velocity, acceleration, and time, and takes out this final velocity. We know that final velocity is the initial velocity plus acceleration times the elapsed time. Because what is acceleration? Well, it's the rate of change of your velocity, right? So your acceleration is your final velocity minus your initial velocity over your elapsed time, right? If that's the case, if acceleration is defined this way, so acceleration is your final velocity minus your initial velocity over your time, because it's your change in velocity per unit time, right? And sometimes I just write this as delta t. Sometimes you'll see tf minus ti. So your final time and your initial time. But I'm just going ahead and writing this as delta t. So it's your change in velocity, your change in time, your elapsed time. That's your acceleration, right? So if we solve for final velocity in this equation, so how will we do that? We'd multiply both sides by delta t, so we'll have final velocity minus initial velocity equals acceleration times elapsed time. We'll add initial velocity to both sides and we'll get final velocity, just initial velocity plus acceleration times your elapsed time. So we can substitute this quantity, initial velocity plus acceleration times elapsed time, in this formula. So we have d equals vi plus vf over 2 times delta t. But we know that, so we have vi, we're just writing that down. We know that vf is equal to vi plus a delta t. This whole thing is divided by 2. Then all of this is multiplied by delta t. So we have 2 vi over 2 times delta t. So that's vi plus vi over 2. This whole, everything's getting multiplied by delta t, right? So this is vi times delta t plus vi times delta t. So that's 2 vi and over 2 times delta t. And then we have this portion here, a times delta t again, but it's also divided by 2. So 1/2 a times delta t squared. 2 vi over 2 is just vi. So we have vi delta t plus 1/2 a delta t squared. So this is one of the formulas for d that'll be really useful for you if you're given a problem asking you to find the displacement and you're only given the initial velocity, the acceleration, and the elapsed time. So they say, for example, a car starts out at 20 meters per second, or let's say a car starts at rest. All right, a car starts at rest in 2 seconds. It's accelerating at 10 meters per second squared. In 2 seconds, how far does it go? We don't know the final velocity. Using this equation, we can solve for the displacement. So I'm just going to rewrite this above, or not above, to the side here. So we have d equals vi delta t plus 1/2 a delta t squared. The question could be worded another way. We could be given the displacement and the initial velocity and the elapsed time and be asked how fast the car is accelerating. So we could say a car speeds up. A car is initially going at, say, 30 meters a second, and in 5 seconds it speeds up. We don't know its final velocity, but it speeds up, and in 5 seconds it goes a distance of, a couple hundred meters. How fast is it accelerating? So in that case, we just solve this equation for a, right? So we would say a is equal to, well, 1/2 a delta t squared is equal to d minus vi times delta t. Okay, so a delta t squared is equal to 2 d minus vi delta t. Then a is just equal to 2d minus vi times delta t over delta t squared. The point being here, if you know any one of these four quantities, or if you know any three of these four quantities, you can solve for the fourth. So this formula here eliminates final velocity. This formula here eliminates final velocity. Let's say we want a formula that eliminates, let's say we want to eliminate elapsed time. And we know that displacement is initial velocity. It's average velocity times elapsed time. But assuming constant acceleration, we know that's initial velocity plus final velocity over 2 times elapsed time. Oops, just got a message, my battery's running low. But let's say we want to eliminate elapsed time. Well, what did we say acceleration was? We said it's the change in velocity per unit time, and so that's v final minus v initial over delta t. If we solve for delta t, we get delta t is v final minus v initial over the acceleration. So now we have something that we can substitute here for delta t. Right. We can substitute this in for delta t. So we get d equals vi plus vf over 2 times vf minus vi over a. So we get d equals vf squared minus vi squared over 2a. And if that doesn't make sense, just pause this video and FOIL this out, and you'll see that this is what that equals. So here, you know, if you're asked a problem about a car speeding up or slowing down, or let's say a car slows to a stop, right? So you know the final velocity, and let's say you're given the initial velocity. You don't know how long it takes for it to slow to a stop, but you know its rate of deceleration. You can find the displacement. Alternatively, if you know how far it moves decelerating, and you know the initial velocity, final velocity is 0 when it slows to a stop, you can solve for the acceleration. So again, you know any three of the four quantities, you can solve for the fourth. So this formula here, this one eliminates delta t, or elapsed time. The initial formula we worked with, like displacement is average velocity times elapsed time, and assuming constant acceleration, that's initial velocity plus final velocity over 2 times elapsed time. This eliminated acceleration, right? So this formula here, it relates displacement, initial velocity, and elapsed time without having to know acceleration. So this one eliminates acceleration, this one eliminates delta t, so this vf squared minus vi squared over 2a. And this one, the vi delta t plus 1/2 at squared, eliminates final velocity. So we've eliminated final velocity. We found one that eliminates elapsed time. And we began with one that eliminates accelerations. What if we want to eliminate displacement? That's one we haven't talked about. Well, our acceleration formula, final velocity minus initial velocity over elapsed time, doesn't seem to have displacement in it. So the formula, we can say acceleration equals final velocity minus initial velocity over elapsed time. We can say this eliminates battery's running really low, displacement, or I'll just say eliminates D. So we have one more formula to derive, and that's one that eliminates initial velocity. We've derived ones that, we started with one that eliminated acceleration, and then we used one that eliminated displacement to find ones that eliminated both final velocity and elapsed time, but we have yet to derive one that eliminates initial velocity. And that's what we're going to do right now. So we know that acceleration equals final velocity minus initial velocity over the elapsed time, right? So we can rearrange this, multiplying both sides by the elapsed time and then adding initial velocity to both sides to get that final velocity is initial velocity, it's acceleration times elapsed time. But it's initial velocity that we want to eliminate, right? So we have to solve for initial velocity. So initial velocity is final velocity minus acceleration times elapsed time. Okay, all I did here was I subtracted a delta t from both sides. And we also know that the displacement is the initial velocity. This is assuming constant acceleration again. Initial velocity plus final velocity over 2 times the elapsed time. And we now know that the initial velocity is final velocity minus a delta t. Okay, and then so to that we're going to be adding the final velocity, dividing that whole thing by 2. This is the expression here for initial velocity from here. Hopefully you see that. So we added final velocity divided by 2, and we're going to be multiplying this whole thing by delta t. So here we have 2 v sub f terms. So we're going to have 2 v sub f over 2 times delta t minus a delta t squared over 2. So we have v sub f delta t minus 1/2 a delta t squared. And this is our final formula here. This is one that eliminates the initial velocity. So if a car is slowing down to a stop, you don't know its initial velocity. You know its final velocity because it's slowing down to a stop, and it takes like 5 seconds to slow down, and it travels 100 meters. Or it takes 5 seconds to slow down, travels 100 meters. You can solve for the acceleration without having to know its initial velocity. So now that we've derived all of the 5 formulas, relating any four of displacement, initial velocity, final velocity, acceleration, and elapsed time, and eliminating one of them, I'm going to go ahead and list all of them cleanly once again. So this is eliminating acceleration. We have displacement is initial velocity plus final velocity over 2 times the elapsed time. Now eliminating displacement, have acceleration is final velocity minus initial velocity over the elapsed time. Now eliminating final velocity, we have displacement is initial velocity times elapsed time plus 1/2 times the acceleration times the elapsed time squared. Now eliminating elapsed time, we have displacement equals the final velocity squared minus the initial velocity squared over 2 times the acceleration. And finally, eliminating initial velocity. We have the displacement is the final velocity times the elapsed time minus 1/2 times the acceleration times the elapsed time squared. And these 5 formulas can pretty much get you through all of one-dimensional kinematics problems. The only things to be wary of are the sign of SIGN of velocity. Usually the problem will establish what the positive direction and the initial and the negative direction are. So usually the direction in which you're starting out is the positive direction. Acceleration also will be important to the sign of acceleration is also important to pay attention to. A positive acceleration usually means you're speeding up, and a negative acceleration means you're slowing down. And note that a negative velocity in the context of one-dimensional kinematics problems typically means that you're heading in the direction opposite to that which you started. So say you start out at 20 meters per second, you're decelerating at -2 meters per second squared, or let's say you're accelerating. So let's say VI equals 20 meters per second, and A is -2 meters per second squared. This basically means that you are slowing down at a rate of 2 meters per second squared. So every second your velocity is going down by 2 meters per second. So in 12 seconds, how fast will you be going? Well, in 12 seconds you'll be going at 20 meters per second plus the acceleration, so plus -2 meters per second squared times 12 seconds. So 20 minus 24, you'll be going at -4 meters per second. So this just means that you will have stopped and turned around, and you'll be heading in the direction opposite to that which you started at 4 meters per second. So really those are the, well, and displacement's also the signs important to pay attention to, because, you know, let's say you're decelerating at 2 meters per second, and I don't know. So now I'll ask you a different question. now we know that, let's say if we had a car that initially was traveling at 20 meters per second and was accelerating at -2 meters per second squared, or really it's slowing down at 2 meters per second every second, we know that at some point it's going to turn around, right? Because we saw after 12 seconds its velocity is -4 meters per second, so it's heading 4 meters per second in the opposite direction. So it starts here, at some point it turns around, and we know that it's going to be, so it's slowing, it's decelerating at 2, it's going pretty fast, right? But then it's slowing down, coming to a stop and turning. But when it heads in the negative direction, it's actually accelerating, right? Because this -2 meters per second squared, let's say, at some point at t sub 1, or I don't know, at some point you're going at 0 meters per second, right? Well, then a second later you're going to be going at -2 meters per second, and the second after that you're going to be going at -4 meters per second. Well, that is 4 meters per second in the opposite direction, so you're speeding up. You're going to be speeding up indefinitely, right? Because this acceleration is a constant, -2 meters per second squared. So eventually you're going to get back to where you started. And let's say we were asked to find that out. Well, we know how to do that now. So displacement is equal to the initial velocity times the elapsed time plus the acceleration plus 1/2 the acceleration times elapsed time squared, right? In this case, the initial velocity is 20 meters per second. The acceleration is -2 meters per second. 1/2 times -2 is just 1. Right, so 1/2 times plus 1/2 times -2 times delta t squared. So that's just 20 delta t minus delta t squared, right? And we're interested, when do you get back? So we said it starts, say it starts here, it goes this direction, eventually turns around, it'll come back. It'll be speeding up in this direction, eventually get back to where you started from. We want to know when it gets back to where you started from. So we'll set displacement equal to 0, right? You'll see we have a quadratic equation here. This is a quadratic. And we can factor, we can pull out delta t. We'll have 20 minus delta t. So 0 is equal to, so you notice that anything times 0 is 0. So either of these quantities can be 0 for this equation to be satisfied. And that happens when delta t equals 0. So initially, of course, you're at your starting point, but also when delta t equals 20, this factor is 0. So you multiply 20 by 20 minus 20, you're multiplying 20 by 0 and you get 0. So at 20 seconds you're back at your starting point. So hopefully you now see how to use these formulas we derived to go about solving one-dimensional kinematics problems.